In 1917, Albert Einstein introduced the cosmological constant, lambda, into his field equations. Positioned on the left side of the equal sign, lambda acted as a property of pure geometry, a structural feature designed to hold the universe in a static state. That static model collapsed when Edwin Hubble proved the universe was expanding. Galaxies were drifting apart in all directions. Seeing that the cosmos was dynamic rather than still, Einstein removed the constant, eventually labeling it his biggest blunder. Modern cosmology eventually resurrected lambda to explain why that expansion is accelerating. However, the constant was moved to the right side of the equation. This reinterpreted lambda as vacuum energy, a local density of fluctuations pushing space apart from within. Shifting the constant to the right side created a massive conflict. The theoretical estimate for this vacuum energy exceeds the expansion we actually observe by 122 orders of magnitude. This is the largest gap between mathematical theory and empirical observation in the history of physics. It is the core of the cosmological constant problem. The 122-order error suggests that treating a global geometric property as a local energy source creates a mathematical mismatch. Resolving this crisis requires us to return to the left side of the equation and re-examine the universe as a geometric whole. We can model cosmic expansion without invoking dark energy or unknown forces. In this framework, the acceleration we see is driven by the inherent shape of the universe. This model treats lambda as a fixed boundary condition. It represents the lowest possible vibration of the cosmic shape, setting a geometric baseline that the universe must follow. This table shows the precision of this geometric approach. By deriding lambda from the cosmic boundary, we reach a value of 1.12 times 10 to the negative 52 inverse square meters, matching the observed value of 1.11 times 10 to the negative 52. This prediction aligns with reality to a margin of 2%. The calculation relies entirely on established topology and differential geometry, requiring no new physics. To prove this value, we will trace an 11-step mathematical chain, starting with the fundamental shape of the cosmos and testing it against independent data from the early universe. If the universe possesses a specific topological shape, the rate of its expansion is a mathematical requirement rather than a mystery. We begin with the most basic shape of a three-dimensional cosmos, S3. This is the unique, simply connected, and closed manifold that serves as the baseline geometry for our universe. Within this space, we introduce a non-oriental boundary. Imagine a single circular loop stretching and folding over itself to form a twisted surface where up and down cannot be globally defined. This twisted shape is a Möbius surface, the unique minimal surface that can be formed from a single circular boundary. We define this as the cosmic boundary. This wireframe sphere shows the boundary scale. We map the boundary loop to the universe's great circle with circumference 2 pi r. Because a Möbius boundary traverses its surface twice, one lap covers half that circle, setting the strip's length at exactly pi r. This twist creates a unique geometric requirement. Moving one full lap around the strip returns you to the exact opposite side of where you started. It takes 2 full laps to return to your original state. This physical twisting dictates the behavior of any field or wave traveling across the surface. It imposes a strict boundary condition that the geometry cannot bypass. Because the surface flips, a wave completing one lap must physically flip its amplitude, creating an anti-periodic boundary condition. It cannot remain unchanged. It must flip its orientation, precluding any flat state, and forcing all permissible waves into a half-integer spectrum. The existence of a Möbius boundary prevents the universe from being static. The geometry itself enforces an active wave state. To find the specific waves allowed on this curved surface, we use the Laplace-Beltrami operator. This tool identifies modes, spatial patterns that the geometry leaves unchanged except for a scale factor, known as an eigenvalue. Observations of the cosmic microwave background show an extremely uniform universe. We must identify the smoothest possible wave allowed by our twisted boundary. That state is the ground mode. It has no internal nodes, meaning it lacks the oscillations that would break the uniformity we see in the early universe. Matching this smooth ground mode to our three-dimensional space requires a totally geodesic embedding. This means the surface has no extrinsic curvature. It is embedded as simply as possible, carrying no extra bending information. This metric equation defines the curved boundary surface. The geometry is determined by radius r, tracking the surface as it bends. Applying our operator isolates the intrinsic surface eigenvalue, reducing the complex geometry down to a single value, 2 over r squared. A mathematical principle called the Bochner identity guarantees that this value is the absolute minimum possible bound. This confirms that 2 over r squared is the true ground state for this topology. This eigenvalue, 2 over r squared, represents the geometric energy built directly into the fabric of the boundary. We have calculated a value for a two-dimensional surface, but we observe the universe as a three-dimensional volume. We need a way to bridge these dimensions. The Gauss-Kodazzi equations act as the translator. They link the intrinsic curvature of a surface to the ambient spatial curvature of the three-dimensional space it lives in. Because our surface has no extrinsic curvature, those terms in the Gauss equation drop to zero, simplifying the relationship. The math reveals a clean ratio. Three-dimensional spatial curvature is exactly triple the curvature of our two-dimensional surface. General relativity provides the final connection. In the late-stage vacuum of the universe, spatial curvature relates directly to the cosmological constant, equal to 2 lambda. By combining these ratios, we find that 2 times the observed lambda must equal 3 times our surface eigenvalue. This reveals a conversion factor of 3/2. Multiplying our surface geometry by this conversion factor gives us the final result for the observed cosmological constant. Lambda equals 3 over r squared. We now move from abstract math to concrete data. We can test the 3 over r squared formula against independent measurements of the universe. The fundamental scale of the cosmos is visible in the cosmic microwave background. By looking at the low multiple cutoff point, we can measure the curvature radius of the universe directly. This background radiation data gives us a curvature radius, r, of 1.64 times 10 to the 26th meters. Crucially, this value is derived without using any of the supernova data used to calculate dark energy. Feeding the measured radius into our formula results in a predicted lambda of 1.12 times 10 to the negative 52nd inverse square meters. Comparing this to the observed benchmark, they align within a 2% margin. The geometric model accurately predicts spatial expansion. Local vacuum fluctuations certainly exist, but they cannot dictate the global properties of the boundary. In this model, the boundary geometry is what sets the expansion rate. The 122 order error was the result of attempting to calculate a global geometric shape using a local energy ruler. To be a valid scientific theory, this model must be testable and capable of being falsified. Because this model is built on fixed topology, it predicts that lambda is a rigid constant. It cannot change or evolve as the universe grows older. The Euclid mission will track expansion precisely. If it detects greater than a 2 sigma variation in lambda across time, this theory is falsified. A second benchmark requires 3 times the observed lambda equals 2r squared within a 3 sigma threshold against radius data. Einstein's original instinct to treat the cosmological constant as an intrinsic geometric property appears mathematically sound. The constant belongs on the left side of his field equations. The cosmological constant has moved from a static placeholder to a rejected blunder and finally to a misunderstood energy crisis. Einstein's constant stands as the structural ground tone of a resonant geometric universe.